afternoon, Bache. Let's start today's class. In this class, we are going to talk about damped oscillations. So far, we have been talking about undamped oscillations, which are your ideal simple harmonic oscillators. They are not realistic kind of scenarios that we face in our day-to-day life. Now we are moving towards a more realistic case, which will be your damped oscillation. So you still have oscillations, but these oscillations have some kind of frictional forces which are acting on your object which is moving here. So what would happen in this case is obvious that your amplitude is going to decrease with time, right? But how your amplitude is going to decrease with time, we would like to have some idea about them. Is your amplitude going to decrease with time as a function of 1 by t? Is it going to decrease as a function of 1 by t square, or is it going to decrease exponentially? How that decrease is going to happen? We'll get the derivation for that. And these kind of oscillations are again called as damped oscillations. So what would happen in this case is that now your energy is going to decrease as a function of time, because if your amplitude is decreasing continuously, then your energy is also being dissipated continuously. An example of that kind of oscillations is, for example, you have a vertical spring which is attached here and a mass is attached to that spring, and if it is put inside some kind of liquid, even if it is in air, that is an example of your damped oscillation, right? Your pendulum, if you are doing it not in vacuum, if you are doing it in your lab, that is also an example of damped oscillation. Now, in the case of damped oscillations, you have some kind of retarding force that is going to act on your object. Now, we are going to make an approximation for that damping force, and we are going to say that this damping force is going to have this kind of expression or this kind of dependence here, where we are saying that your damping force or the retarding force is directly proportional to negative of velocity. We are saying that more is the velocity, more will be your retarding force, and your retarding force is always going to act in a direction opposite to the velocity of the object. That is why there is a minus sign here. To remove this constant, this sign of proportionality, a constant is introduced, and that constant is B, which is called as your damping coefficient. B can be large, B can be small, depending on the medium in which you are having your damped oscillation. Now, question is that, is this expression universally true? No, this is not universally true. This expression is most valid when your object is moving in fluids, which basically means that if your object is moving in liquids or gases, in that scenario, this expression is valid. The second assumption is that your object is moving with a velocity which is not very large. आपके जो object की velocity है, that is small. That is the second assumption in this case. But this is the best example that we could get for the retarding force in this case. So if you take this force also into account, in the previous case, when you had an ideal SHM, then you said that your force is equal to minus kx. Now, on the top of this restoring force, you have an additional force also. So now you would say that, just give me a second. Someone is very eager to write on the screen. Now, in this expression for force, we have to add another term also, and that another term would be your this retarding force that we have just talked about. So this would be your expression for force. Now you have a restoring force, but with the restoring force you also have a retarding force, which is given by this expression over here. Similar to the previous case of ideal simple harmonic oscillator, we are going to write our acceleration as second order derivative of position. That would be equal to minus kx minus b, velocity is dx by dt. Take everything on the one side. This is what you will be getting. You will have m times d2x over dt2 plus b dx over dt plus kx is equal to 0. Divide throughout by m, which is the mass of the object. This is what would be your final expression over here. Now, these kind of equations, I'm not sure if you are familiar with, but these kind of equations are called as second order differential equation. And maybe you will read in math, but for the solution of these kind of approximations, you make some kind of educated guess about what could be the possible solution for these kind of equations. And for this particular kind of equations, usually your first guess would be that your solution would be of this form here. It would be some exponential function. If I say that this is my solution here, where a is some constant and alpha is also some constant. Both of these are constant that we don't know as of now. We will determine them later. Now, if I say that, okay, this is my guess that probably this would be solution to this above equation here. In that case, if I'm saying that this is the solution of this equation, that means this value of x should satisfy this equation, right? For that, I have to take dx by dt and I have to do the second order derivative of x with respect to time. If you do that, your dx by dt will be a times alpha e raised to power alpha t, and your d2x over dt2 would be given by this expression here. Now, let's go back to this equation and plug in the value of dx by dt and d2x by dt2. Let's see what do we get here. In that case, this is your d2x over dt2, b over m, dx by dt is your this expression, which is written over here, plus k over m a e raised to power alpha t is equal to 0. A e raised to power alpha t is your x here. From this expression, you can take a e raised to power alpha t common out, right? It's there in all the three terms. If you do that, this is what you will get. Now, there are two scenarios. Either your this term is equal to 0 or the term within the bracket is 0. If you say that this term is equal to 0, that means your x is permanently equal to 0, which would be a trivial solution, which is not an interesting solution from our point of view. Ritu, please mute kar dijiye sabko. That would mean that the term within the brackets is equal to 0.
Excuse me, ma'am.
मैम आप भी म्यूट हो गए.
Yeah.
मैम आप भी म्यूट हो गए हैं, प्लीज.
हाँ जी, मैंने अपने आप को कर दिया अनम्यूट. You can hear me now, right?
Okay.
Okay. So now if you are saying that your this term is equal to 0, which basically means that your a simple quadratic term is equal to 0. And we all very well are aware of solution of these kind of equation, right? आप quadratic term equation का solution बहुत easily find out कर सकते हो. Another thing is that when you will do probably this kind of second order differential equations in math, you will realize that these equation that you finally get this quadratic equation, this is called as characteristic equation, and this is a quadratic equation. If my this term is equal to 0, you can easily get this roots of this equation, right? If you have a simple quadratic equation of this form, bx plus c is equal to 0, you say that your x would be equal to minus b, which is this term over here, plus minus b square, square of this, minus 4 times ac. 4 times a is 1, c is k over m, divided by 2a. A is 1 here. So now this is going to be a solution. You have plus and minus sign here, right? Another thing that has been done over here, just this 2 has been taken care of in the numerator itself. We'll see that why we have done that. You'll see that very shortly. So I'll get something minus b over 2m plus minus, if I take 4 common out from here, square root of 4 would be 2. 2 would cancel each other out, and here you will have b upon 2m whole square minus km. The reason we did take 4 out here so that you can get this expression here, k over m. Remember from your ideal simple harmonic oscillator, k over m was equal to your omega square, right? That's how we defined our omega square. So that's why we have taken 4 common out from here. If you further go, I can say that there are 2 roots now. One root will have the plus sign here and the other root is going to have the minus sign in between. These will be 2 roots. But I said that the solution of this equation was of this time. Now, of course, either of your alphas, whether it's alpha 1 or alpha 2, I have defined alpha 1 where we have retained the plus sign here, and I have defined alpha minus as alpha 2 where you have retained minus sign here, right? So because these two terms are separate from each other. Now you have the solution. Either one of these is going to be a solution. If you say that this term is a solution of your equation that we started with, the second order differential equation that we started it, which is your this equation, d2x over dt2. So the solution of this equation is going to be x is equal to a e raised to power alpha 1t. That is going to be its solution. Similarly, you are this another term, and now since we are talking about two different alpha 1 and alpha 2, it's better to define the constants also separate here. So your this term is also going to be solution. Both of these terms will be solution of this equation. You can go back and plug in the value of alpha 1 and alpha 2 here, and you will see that they will satisfy this equation. Both of these terms are solution. But if you talk about the most general solution, if you have 2 roots for any equation, then there is something which is called as most general solution, and that would be a linear combination of both the solutions, which basically means that you can simply add these two terms over here. Remember, in the case of simple harmonic oscillator, ideal simple harmonic oscillator also, we said that your solution can be a sine function, it can be a cosine function, or it could be a linear combination of both the functions. We can take any of those as the solution for your ideal simple harmonic case. Similarly here, your first term, I'm repeating that again, your first term is a solution, your second term is also a solution. But if you talk about the most general solution, that would be linear combination of both the terms. And that is why we are saying that this would be now my solution here for that second order differential equation that we obtained in the case of damped oscillation, where your alpha 1 and alpha 2 are defined here. I'm stressing on alpha 1, alpha 2 time and again because there is some physical relevance attached with these two terms here. Now, plug in the value of alpha 1 and alpha 2 here. You have alpha 1 multiplied by t, so you will have e raised to power minus bt upon 2m plus square root of whole of this term. K over m has been replaced by omega naught square. Here I have defined omega naught as your frequency for undamped oscillation. I would like to relate my frequency for damped oscillation with this frequency. If I can find some kind of relationship between my frequency for a damped oscillator with an undamped oscillator, that would be a very good expression. So that is why we have put the value of k over m as omega naught square, and this is further multiplied by t here. Similarly, the value of alpha 2 has been put here, and you get this expression over here. So this is going to be now our starting point. I'm going to talk about different kind of damped oscillation, and for each oscillation, this solution is going to be our starting point. I'll start with this value of x. Though I haven't written it, but now I am assuming that you know that this x is now actually a function of time. You know that by default, right? Because you have the time dependence in your solution. So your x is a function of time here. Again, this is your solution here. Now I'm going to talk about 3 different cases here. First case, in the case when your this expression b upon 2m square is greater than omega naught square, right? So your square root term in both of the cases will be positive terms. This will be also positive term and this will also be positive term, right? This is the positive term because remember you are adding, you have e raised to power minus b upon 2mt, and then you are adding into something which is less than b upon 2m, right? If you take the square root of b upon 2m whole square minus omega naught square, this is always going to be less than b upon 2m. And that's why I'm saying that your this term would be some e raised to power minus expression multiplied by t. Similarly, for your second term also, you have minus here, minus here. This is also going to be some exponential function, an exponentially decreasing or decaying function. So if your b upon 2m whole square is greater than omega naught square, that means, remember, b we defined as damping coefficient. So this basically means that your resistive forces or the resistive term dominates your stiffness parameter, which is associated with omega naught. And you will have an overdamped or deadbeat system. This is called as your overdamped system and also called as deadbeat system. Now, the second case, the second possibility is that if both of these terms are equal to each other, in that case, what would happen is that your solution would be something a1 e raised to power minus b upon 2mt plus a2 e raised to power minus b upon 2mt. Usually, I wouldn't go into the details of that scenarios if your roots are equal. In this case, we are saying that both of your roots are equal. In that case, the solution usually you take is of the form a1 plus a2t multiplied by e raised to power minus b upon 2mt. So, but I'm not going to go into the details of that. But
Excuse me,
as far, Hanji,
ma'am, Palam Sharma raised a hand. We want to ask the question.
Hanji, बताइए.
Excuse me, ma'am.
Hanji.
Ma'am, actually, the damped oscillation are new to us. So, can you please teach us little bit slowly and tell us again from the solution of the equations?
You're saying that since this is new, you want me to repeat it?
Yes, ma'am. And can you please teach slowly, ma'am? Little bit slow the speed. It's
Okay,
being very
sure.
fast, ma'am.
I can do that. We are talking about damped oscillations. That means there are some kind of resistive forces that are present in your system, and these resistive forces are going to act in the direction opposite to the velocity of the object. And hence, this would be the expression for your resistive forces. The term B here is a constant of proportionality, and we are calling it as a damping coefficient. B is going to depend upon the medium in which you are having your oscillation. For example, अगर आपने spring को vertically hang किया, उस पे आपने mass hang किया है, उसको आपने air में लिया है, उसको आपने water में dip किया है, depending on that, your B will be different. It's a function of medium. B is called as damping coefficient. अब आपकी जो equation होगी, in the ideal simple harmonic oscillation, we said that आपका force will be equal to minus kx. Now, आपके जो net forces होंगे, उसमें अब आपको अपने resistive forces को भी account में लेना पड़ेगा. We said that force is equal to mass into acceleration, and your acceleration is basically second order derivative. अगर मैं इस वाली टर्म को भी इस साइड में ले आती हूँ, I can write it as kx plus b time dx over dt is equal to 0. टर्म्स को अगर मैं रीअरेंज करती हूँ, प्लस b over m dx over dt प्लस k over m x is equal to 0. इसको मैं ऐसे भी राइट कर सकती हूँ. ये वाली जो इक्वेशन है, ये आपकी सेकेंड ऑर्डर डिफरेंशियल इक्वेशन है. इसके आपके जब आप इसको सोल्व करेंगे तो इसके दो सॉल्यूशंस आएंगे. These two solutions, ये जो मैथमेटिकल इस तरह की इक्वेशंस होती हैं, what you do is that you start with and kind of educated approximation. You start with that, I think this could be the solution of this equation. And for these kind of equations, आपका जो most educated guess हो सकता है, that is an exponential function. You say that इस kind की equation का जो solution होगा वो that would be an exponential function. Right now, we are just saying that a and alpha are some constants, जिनकी value हम बाद में decide करेंगे. I am not saying alpha is real or alpha is imaginary. I am not commenting on that also right now. Alpha could be real, it could be imaginary also, but it is a constant. If I am saying that this is solution of your equation, that means this should satisfy this equation. That's what we have to do in the next step. So take the first order derivative of x with respect to time, dx by dt अगर आप करोगे तो ये आएगा. अगर आप इसका फिर से derivation करोगे तो आपके पास d2x over dt2 आ जाएगा. That would be again one more alpha will come out. You will have a alpha square e raised to power alpha t. dx dt d2x dt2 की वैल्यू अगर आप इस इक्वेशन में पुट कर देते हैं, right? That's what you will get here. A e alpha square e raised to power alpha t plus b over m dx by dt की आपकी वैल्यू ये है, plus k over m multiplied by x, x की वैल्यू आपकी ये है. This is equal to 0. Because we started with saying that कि ये जो है ये हमारी इस equation का solution है. That means this value of x should satisfy this equation. Then only it could be a solution of this equation. And that's what we have done here. अब आप इस equation में से you can take a e raised to power alpha t common, right? It's there in all the three terms, so you can take it out. If you do that, this is what you are going to get. Now you have multiplication of two terms which is equal to 0, which basically means that either the first term is 0 or the second term is 0. If you say that my first term could be 0, but this is equal to your x. So this means that if you are saying that this is equal to 0, this basically means that your x is permanently equal to 0. If your x is permanently equal to 0, then how oscillation is possible, right? अगर आपका x कुछ finite number होगा तभी तो आपका oscillation होगा. X is equal to 0 corresponds to your equilibrium position, right? So you cannot have this condition possible. The second possibility is that आपकी जो within brackets term है that is equal to 0. If that is equal to 0, this means that your alpha square plus b over m multiplied by alpha plus k over m is equal to 0. This is a quadratic equation. इस वाली equation के solution के साथ you might not be very familiar with, but this equation you know very well कि इसका आपको solution कैसे निकालना है. ये जो equation है इसको इस particular second order differential equation की characteristic equation भी बोला जाता है in mathematics. So if you don't know it, that's also fine. It's not of any relevance here if it is called characteristic equation or no. As far as we are concerned, we did get a quadratic equation which we can easily solve. For this equation, if you solve, the roots would be alpha would be equal to minus b, which is in this case minus b over m plus minus b square b upon m whole square minus 4ac. A is 1, c is k over m. So you will have minus 4k over m divided by 2a. So you will have 2 in the denominator. 2 को आप ऊपर ले जाइए, you will get minus b upon 2m. इस वाली जो equation है square root में से अगर आप 4 कॉमन निकालते हो तो यहाँ पे आपको 4 से मल्टीप्लाई करना पड़ेगा and 4 से डिवाइड करना पड़ेगा. उस 4 को I can take inside as 2 and then 2 का square would be basically a 4. So that now you have 4 here, take that out, you will have 2 upon 2, that would be cancelled. So you will have something of this form here. You have two roots now. One which will have the plus sign, that's called as alpha 1, and the second one which will have the minus sign here, that let's call that as alpha 2. अब आपके ये दो हैं, ये रूट्स हैं इस इक्वेशन के। हमने कहा था that this is your solution that we started with, right? But now your alpha can have two values. रितु कौन बोल रहा है?
Rohan ma'am, I will. Rohan, you want to ask something?
रितु म्यूट कर दीजिए, किसके बैकग्राउंड से आवाज आ रही है?
Okay ma'am, okay.
So we said that this is going to be a solution, but now we came to know that alpha can have two values. Now either one of alpha is going to be solution of your quadratic equation. आपकी जो quadratic equation थी, which was this equation, d2x over dt2 plus b over m dx over dt plus k over m x is equal to 0. For this equation, we said that this is our approximation or our idea of solution. Now we are saying that alpha can have two values. So this can be a solution of this equation, and this can be a solution of this equation also. But the most general solution would be a linear combination of both the solutions. I'm repeating that again. In the case of ideal simple harmonic oscillator also, we said that sine can be solution, cosine can be solution, or a linear combination of both of them also can be solution. Similar to that, here your this term is also a solution, this term is also a solution. But if you talk about the most general solution, your most general solution is going to be a linear combination of both of the terms here. Here now a1 and a2 are two constants, the value of which we don't know as of now. आपको जब initial conditions दी जाएंगी, at time t is equal to 0, this was your value of x and this was your value of velocity. Based on that, you can calculate the value of a1 and a2, the constants. But we know what is the value of alpha 1 and alpha 2. We have calculated that, right? If you look at the value of alpha 1 and alpha 2, you know the damping coefficient, आपको mass भी पता है, आपको spring constant भी पता है. So you can calculate what can be the value of alpha 1 and alpha 2 in this case. Plug in the value of alpha 1 and alpha 2 in this equation here, right? a1 e raised to power minus b upon 2m t. You have to multiply alpha 1 by t. So I'm taking that out, plus within the brackets, I'm taking this whole term and I'm multiplying this also by t, and I have multiplied this by t. This is your now your alpha 1 t, which was your solution. Similarly, for alpha 2 t, this would be your solution. And I can take this in the brackets and multiply it by t. This is what has been done here. I would like to get an idea of the frequency of the damped oscillation. Just give me a second. Now, in this case, where was I? I would like to get the expression for damped oscillation frequency in terms of undamped frequency. We know what was the frequency for an undamped case, right? That was given by your omega naught, and your omega naught we defined to be equal to square root of k over m. I would like to know what is the frequency for the damped oscillation. So that is why I have done here omega naught square compared with Hanji Mayank. उनको एक बार अनम्यूट कर दीजिए रितु.
Yes ma'am.
एक्सक्यूज मी मैम.
हाँ जी.
तो ओमेगा नॉट जो हमने लिया, तो
Yes.
वो ओमेगा नॉट वही है जो अनडैम्प्ड में होता है.
Exactly. This is the same. अगर
अच्छा, और
आपका
अब यहाँ से
resistive
हम
forces 0 होते, हाँ जी,
यहाँ से अब हम रिलेशन निकालना चाहते हैं ओमेगा नॉट और ओमेगा डी पे।
yes, eventually
ओके
that would be our aim.
ओके मैम।
Okay, राहुल बताइए। राहुल कामरा। Now these are our two solutions. One which will consist of alpha 1, the second one which consists of alpha 2. रितु ये कौन है, आप प्लीज इसको रिमूव कर दीजिए।
राहुल कमरा मैम करती हूँ मैं इसको।
हाँ जी, इसको क्लास से रिमूव कर दीजिए।
जी मैम।
Now we can have three different cases, right? What we can have is that the term within the brackets, the term which are outside the brackets, we are very clear about those terms. These are some kind of exponential decaying functions here. Now, if these are going to be exponentially decreasing, exponentially increasing, we want to decide that. And that would be basically decided by your terms within the bracket. Your terms within the bracket, if I say that your b upon 2m whole square is greater than omega naught square, then since your b is associated with resistive forces, b we defined as damping coefficient. That means we are saying that कि आपके जो resistive forces हैं, they are dominating your restoring forces. उस केस में क्या होगा? If you look at this term here, यहाँ पे तो आपका इसके minus में you are still having some term which is minus of this term. So this is definitely going to be some exponentially decaying function of time, right? The second term here. Now in the first term where you have the plus sign here, but आपकी जो term within the brackets है, this is always going to be less than this term. The reason I'm saying that, I'm claiming that your this term, if I take square root of this term, this would be always less than b upon 2m, right? If this is always less than b upon 2m, I'm further having multiplication of this term with t. So even if it's plus here, effectively you will still have an exponentially decaying function here also. The solution for this equation in this particular scenario, when your b upon 2m square is greater than omega naught square, will have both the terms as exponentially decaying function. So what would happen is that if you plot your x as a function of time, it would simply will be a sum of two exponential functions, and both of them are exponentially decaying function. Now if you talk about the second scenario, in the second scenario I'm saying that, let's say that these two terms, they are equal to each other. Your b upon 2m square is equal to omega naught square. Your this term would become 0. Where is my pen? This term would become 0. This term also would become 0.
Excuse me ma'am. Neeraj Bansal raise a hand.
हाँ जी, बताइए नीरज।
एक्चुअली मैम फर्स्ट केस में आपने बताया कि डैम्पिंग रेजिस्टेंट टर्म्स डोमिनेट स्टिफनेस टर्म, इसका आप मेरे को एक बार मीनिंग बता देंगे मैम कि कैसे? समझ नहीं आया, वो आपका समझ आ गया कि एक्सपोनेंशियली डिक्रीजिंग टर्म होगा, वो समझ में लग गया, लेकिन ये लाइन नहीं समझ में लग रही। डैम्पिंग रेजिस्टेंट टर्म्स डोमिनेट।
आई एम सेइंग दैट आपका जो b है, that is related with your damping forces, right? When I'm saying this is greater than this, basically I'm saying that this is greater than k over m. This is what I'm saying, right?
Right ma'am.
K is connected with your spring constant, which is related to your restoring force, right?
Yes
B
ma'am.
is your damping coefficient, which is related to your retarding force or resistive forces or dissipative forces, whatever you want to call that.
Okay.
And hence, from here, then we can say that your retarding force is going to dominate your restoring forces in this case.
Okay, it means that retarding force dominate
अगर आपका
इसका
okay,
मतलब कि जो रिटार्डिंग डोमिनेट स्प्रिंग कॉन्स अरे यार स्प्रिंग जो फोर्स लगाएगा वो कम हो जाएगी रिटार्डिंग फोर्स से.
एग्जैक्टली एंड दैट इज व्हाई आपका जो सॉल्यूशन आएगा वो एक एक्सपोनेंशियली डिकेइंग फंक्शन आएगा. अगर आपका स्प्रिंग कांस्टेंट डोमिनेट करता which basically means that you are saying that your restoring force is dominating, तो आपका फिर भी oscillation होना चाहिए था, right? This is what happens in your pendulum case. एयर का रेजिस्टेंस कम होता है, right? तो आपका जो restoring force है वो dominate करता है and that is why आपका pendulum है वो decreasing amplitude के साथ में still oscillate करता रहता है. But
okay.
when you are saying that your retarding force is dominating your restoring forces, in that case restoring force basically causes oscillations, right? आपका रिटार्डिंग फोर्स डोमिनेट करता है तो वो आपके रिस्टोरिंग फोर्स की वजह से जो ऑसिलेशन होने चाहिए थे इट डजंट लेट देम हैपन.
तो फिर मैम वो जो अपन स्प्रिंग स्ट्रेच करके रखते हैं वो वहीं पे रहेगा ऑब्जेक्ट फिर ऑसिलेशंस तो क्योंकि होंगी
नहीं. आपका ऑब्जेक्ट की अगर आप निकालो, फॉर एग्जांपल आपने जो पेंडुलम को एक एक्सट्रीम में ले जाके अगर रिलीज कर दिया, लेट्स टॉक अबाउट मोर रियलिस्टिक केस, तो वो पेंडुलम क्या होगा, वो बहुत स्लोली आता रहेगा इवेंचुअली अपने इक्विलिब्रियम पोजीशन पे, hypothetically at time t is equal to infinity. Remember आपका exponentially decaying function है, तो when t tends to infinity your x will tend to 0. So hypothetically at t is equal to infinity आपका pendulum जो है वो equilibrium position पे आके stop हो जाएगा.
ठीक है. Okay.
That would be the meaning of this.
Okay, thank you ma'am.
Welcome बच्चे.
नेक्स्ट वन इज मैम आदित्य.
हाँ जी आदित्य बताइए. आदित्य. बाकी लोग मयंक या करण आप में से.
यस मैम. मैम तो जो आपका फर्स्ट केस आपने बताया,
हाँ जी बच्चे.
उसमें ऑसिलेशन नहीं होगा फिर?
नहीं, there is no oscillation. I'm going to show you the graph for that also. There is no oscillation. Over damped and the second case critically damped. इन दोनों में कोई oscillation नहीं होता है. So ideally it's wrong to call them oscillatory motion क्योंकि कुछ oscillate करता ही नहीं है. वो बस अपने equilibrium position पे आके stops there.
एंड मैम तो अगर हम बाई चांस जैसे आप बोल रहे हो स्प्रिंग फोर्स को ज्यादा होना चाहिए रेजिस्टिव फोर्स से,
Yes.
तो उसके लिए तो ओमेगा नॉट स्क्वायर ज्यादा हो जाएगा.
हाँ जी. That's what the third case. I'm going to talk about that now.
ओके मैम. ओके मैम. थैंक यू मैम.
हाँ जी.
नेक्स्ट इज करण.
मैम एक छोटा सा डाउट था कि मैम द डैम्पिंग फोर्स इज अपोजिंग द रिस्टोरिंग फोर्स, राइट मैम?
Yes.
So ma'am, but in the beginning we talked about that ma is equals to minus kx minus bv. So ma'am, from here aren't they in the same direction? Both
What
negative.
is in the same direction?
The restoring force and the damping force. Ma'am, in the beginning you wrote that ma is equals to minus.
सेम डायरेक्शन में ही है.
One is against, one
Yes ma'am.
tries to bring it back to equilibrium. The second one is against the direction of velocity. So these are two different terms. एक displacement में है, एक velocity में है.
Okay ma'am, so they are actually opposing each other. Okay.
Yes.
Ma'am. Clear now. Thank you ma'am.
Welcome. Again, if I go very fast at any point, like today, you can stop me because many times I don't realize that there are certain things which you are doing for the first time. I can repeat them time and again. That's okay with me. So the second case, we are saying that these two terms are equal to 0, which basically means that if you go to the previous slide, if your this term is 0 as well as this term is 0, you are saying that both of the alpha 1 and alpha 2 they are equal to each other. अगर आपका b upon 2m square is equal to k over m, तो आपका alpha 1 is also minus b upon m, alpha 2 is also minus b upon m. Both of them are equal to each other. But I'm not going to again go into the details of that. Usually इस case में आप क्या कहते हो कि rather than saying कि okay both of the roots are equal, you say that in that case आपका जो general solution होगा that would be of this form. A2 multiplied by time e raised to power minus b upon 2m multiplied by T. Something like this. You don't have to bother about this solution. So this is kind of extra information. You can store it somewhere else. But in the case, as far as you are concerned, so when these two terms are equal to each other, your x is still an exponentially decaying function. So in this case also, there will be no oscillations and your object will come back to its equilibrium position after certain amount of time. And this is called as your critically damped system. The third case, which we are going to talk bit in detail, says that if your b upon 2m square is less than omega naught square, what would happen in that case? So let's talk about this a bit in detail here itself. In that case, I can rewrite these terms within the bracket in this form also. I can say that I'm going to write it in this form. And this way I can write only for the third case. This kind of scenario or this kind of solution is not general. ये आपका सिर्फ थर्ड केस में होगा when you are saying b upon 2m square is less than omega naught square. That means ये वाली टर्म आपकी हमेशा नेगेटिव आएगी. उस नेगेटिव को अकाउंट में लेने के लिए मैं पहले ही इनका ऑर्डर रिवर्स कर देती हूँ. -1 मैं बाहर ले देती हूँ. -1 का स्क्वायर रूट आपका आयोटा आ जाएगा एंड यहाँ पे मैं इनका ऑर्डर जो है वो रिवर्स कर देती हूँ. And this would be further multiplied by time. Similarly, for A2 multiplied by e raised to power minus b upon 2mt minus iota further omega naught square minus b upon 2m square multiplied by t. अब आप इसमें से what you can ideally do is that
Excuse me, ma'am.
हाँ जी.
Tarun raised a hand.
हाँ जी तरुण बताइए. तरुण.
हाँ मैम, मैं कहना चाहता था, आई एम स्टूडेंट ऑफ थर्ड. एक्चुअली मैंने बैकलॉग सब्जेक्ट लिया है यूपीए 001. ये मेरी फर्स्ट ही क्लास है. सो आई वांटेड टू से कि आप अगर मेरा नाम नहीं है लिस्ट में, लिस्ट ऑफ स्टूडेंट्स होगा आपके पास, तो उसमें प्लीज मेरा नाम ऐड कर लीजिए. और
दैट वुड बी डन ऑटोमेटिकली. आप सभी लोगों की जो अटेंडेंस है वो बैक एंड पे जूम पे रिकॉर्ड होती रहती है. वी डोंट हैव टू ऐड एनीथिंग, राइट? सो उसमें वो ऑटोमेटिकली आपका नाम दिखा देगा.
कि जैसे कि सीआर या जीआर है इस ग्रुप का, तो उसकी कांटेक्ट डिटेल्स प्लीज मुझे मिल जाती, क्योंकि जैसे क्विज होता है या फिर कोई लैब वैल्यूएशन होती है तो मेरे को पता नहीं चलेगा, मैं ग्रुप में नहीं हूं ना इनके.
ओके, आप मेरे को एक सेपरेट ईमेल कर दीजिए या मैसेज कर दीजिए.
मैम आपकी मेल बोल सकते हैं आप प्लीज एक बारी?
बच्चे वो बाद में आफ्टर द क्लास आप अपने सीआर या ग्रुप से ले लीजिए. जस्ट ए सेकेंड.
ओके मैम.
ओके, सो व्हाट यू कैन डू इन दिस केस इज दैट ये जो आपकी ये वाली जो टर्म है, जो आपकी कॉमन टर्म है दोनों में, यू कैन टेक इट आउट एंड फिर आपके पास में e raised to power iota something, this we are going to call as your damped frequency omega d. e raised to power iota omega t बचेगा multiplied by t plus a2 e raised to power minus iota omega dt, and this will be multiplied by e raised to power minus b upon 2mt. एंड यहाँ पे आपके पास a1 भी होगा. अगर आपके पास रिमेंबर साइन और कोसाइन जो फंक्शंस होते हैं उसको आप e raised to power iota x की फॉर्म में लिख सकते हो, राइट? e raised to power iota x you say is cos x plus iota times sin x. Similarly in this case also these terms, ये जो विद इन ब्रैकेट मैंने टर्म्स लिखी हैं, ये आपका ऑसिलेशन प्रोड्यूस करती है इन द केस ऑफ अनडैम्प्ड ऑसिलेशन. And in this scenario, you will say that your system is lightly damped. You will get an oscillatory motion here. और अगर आप there is a mathematics involved in it, I can provide you with the details of mathematics, but अगर आप इसका in general solution लिखना चाहें इस केस में, you will write that your x as a function of time would be equal to a e raised to power, ये वाली जो आपकी कॉमन टर्म आपने दोनों से बाहर निकाली थी t, और ये जो एक्सपोनेंशियल टर्म्स हैं e raised to power iota plus e raised to power minus iota, इसको मैं कोसाइन में लिख सकती हूँ। और ये वाली जो कोसाइन टर्म्स है ये आपके मोशन में ऑसिलेशन प्रोड्यूस करेगी, और ये वाली जो टर्म है दैट वुड बी बेसिकली योर एम्पलीट्यूड। आपका एम्पलीट्यूड है वो एक्सपोनेंशियली डिके करता जाएगा। पेंडुलम आपने लिया, साइड में आप लेके गए, रिलीज किया, इक्विलिब्रियम में आएगा, वो दूसरी साइड में जाएगा, उसका एम्पलीट्यूड है वो डिक्रीज हो जाएगा, फिर सेंटर में आएगा, फिर दूसरी साइड में जाएगा, एम्पलीट्यूड उसका फिर से डिक्रीज होगा, एंड सो ऑन। This is called as your underdamped system, and this is the only scenario in which you will actually have oscillation. Overdamped और critically damped system में आपका system oscillate नहीं करता है. Only in the case of underdamped system, your object is going to oscillate about its equilibrium position, and which is what is we are going to discuss probably in the next class. नेक्स्ट क्लास में देखो आप, दिस इज योर अंडर डैम्प्ड कंडीशन, आपका एम्पलीट्यूड आप यहाँ से स्टार्ट करोगे, डिक्रीज होता चला जाएगा कंटिन्यूस, एंड इट विल कीप ऑन ऑसिलेटिंग, एंड फाइनली आपका इक्विलिब्रियम पोजीशन पे वो जाके स्टॉप हो जाएगा। दो लोगों ने कंसर्न रेज किए हैं, बच्चे जरा फटाफट बता दीजिए, इफ आई कैन आंसर इट विद इन अ सेकंड, आई अदरवाइज इन द नेक्स्ट क्लास हम लोग फिर आपके डाउट्स लेंगे।
मैम पीपीटी अवेलेबल है इसकी एलएमएस पे?
बच्चे इसकी पीपीटी ऑलरेडी एलएमएस पे हैं।
ओके मैम, ओके, थैंक यू।
हाँ जी, बाकी लोग ऋषभ एंड गौतम।
मैम मेरे को छोटा सा क्वेश्चन था, एलसी ऑसिलेशन में जब हमें क्या कहते हैं इंडक्टर में मैग्नेटिक फील्ड बनती है, तो उस मैग्नेटिक फील्ड की डायरेक्शन कैसे पता चलती है कि कौन सी
वो आपके
मैग्नेटिक फील्ड
करंट
कब
पे
आएगी?
डिपेंड करेगी बच्चा, आपका करंट डायरेक्शन चेंज करता रहेगा एवरी
मैम
टाइम
जैसे
कैपेसिटर चार्ज और
क्या
डिस्चार्ज
कहते
होगा।
हाँ जी वो तो ठीक है, जैसे अगर करंट के डायरेक्शन के साथ साथ चलेगी मैग्नेटिक फील्ड,
करंट की डायरेक्शन में आप अपने राइट हैंड की फिंगर्स को कर्ल कर लीजिए, थंब आपका मैग्नेटिक फील्ड की डायरेक्शन दे देगा। हाँ जी
मैम लास्ट क्लास की भी पीपीटी अवेलेबल है एलएमएस पे?
हाँ जी, पूरे एसएचएम की एक ही पीपीटी है जो आपके एलएमएस पे मेरे नाम के अंडर जो क्लास लेक्चर है उस पे अपलोड कर दी गई है। सो आगे वाले लेक्चर्स की भी पीपीटी ऑलरेडी अवेलेबल है, अगर आप लोग चाहें तो आप लोग क्लास में आने से पहले यू कैन जस्ट हैव अ वेरी उस पे आप एक नजर मार के आ सकते हो क्लास में आने से पहले।
ओके, थैंक यू मैम।
हाँ जी, इट्स अवेलेबल देयर ऑन एलएमएस। अगले 5-6 लेक्चर की तो कम से कम है ही है।
And we should log out because it's already one
Yes.
o'clock.
Yes, doing that.